I'm Shinichi from NanoQT, so we are from Japan. Whoa, why is it? All right. So I'm a hardware quantum guy, so if anything's unclear, just ask me later or just stop me during the talk. So NanoQT is a startup in Japan developing hardware with what's called optical cavity QED. That's a kind of interface between atom qubit and photonic channels. So that's basically the interface for large-scale QPU, like ones developed by QED, to be connected to the internet. So that's going to be a pretty crucial ingredient for like scaling up the quantum internet. And we're going to say that it's going to be a pretty nice high-speed network hardware solution. So there are plenty of things you can do once you connect your QPUs to your quantum network. And on the flip side, that's also what you need for scaling up QPUs, I have mentioned. And the bottleneck of that, we believe, is this network to qubits inside your module. So modules are either in like cryogenic environment or in vacuum chamber. So you need to integrate quite well with these systems. And to give you a context of the speed, the gate time is mostly like microsecond for superconducting atomic qubits. And QEC cycle time is like these megahertz or kilohertz for atoms in superconducting qubits. And one thing to note is these are parallel for all the qubits you have. So if you scale up your QPU, you have to manage your system so that you can operate everything at once. And that's a like necessity for your FTQC. On the other hand, network interface is really slow at the moment. So for atoms and ions, which is kind of one of the leading platform, the network rate, like entanglement generation rate across network, is less than kilohertz. So it's already slower than these operations. And the error rates are pretty bad compared to the local gates. Like gates are like 99.9% fidelity. Network is less than 98%. And another thing is these are sequential. If you have one channel, you're creating one entanglement at a time, and you cannot like do multiple at a time. So it's limited by the number of channels you have and also the speed of your individual channels. So you have to scale both the channel numbers and also the speed of your individual channels to really keep up with your computation. Otherwise, your network is too slow. It's like having a network from 1990s now with your modern computer. So you're gonna struggle with it. And the network interface, like how fast you can communicate, comes down to physics. I will just briefly talk about the surface of it. But currently, what's done mostly is you're collecting photons from atoms or ions to create networking. And this is like, efficiency is limited because the atoms are emitting photons everywhere, but you're collecting like finite fraction of it with finite size lenses and optical fibers. And on the other hand, what's called optical cavity QED, you are placing two mirrors around a qubit so that you are bouncing light back and forth. And this, like a quantum mechanical system, allows you to increase the efficiency of extraction of your light because your atoms are emitting only in this single cavity mode that you can couple effectively to optical fiber. And the speed of emission is also increased by this increased interaction. And the rate is around a megahertz, like a atom-photon coupling rate. So that's going to be the speed of your network. And there are other things to play with, like direct gate operation between photon and atom qubit. So you can do CZ gate between the two modalities. And say, for example, you can load your information coming through a channel to your local computer and so on. So that's pretty interesting. And so that's again physics, but we have a few ideas on what to do with networked neutral atom QPUs. And one idea is using what's called Ethereum atoms. So they have direct telecom band transition, whereas other species mostly have near infrared, which is not really good for long distance communication. So we think this is pretty good for both long distance communication and also scaling up like local network using connecting QPUs. And they're good for FTQC, and gate fidelities are good. Clearance time is like tens of seconds compared to microsecond gate time. So that's a promising qubit platform. And in terms of scaling up your number of channels, most cavity QED systems are free space cavity. That's what we call. You have bulky mirrors facing each other in the chamber, and you cannot put like many of them in the chamber. So you are limited to just one or two channels. Whereas what we have is what's called nanofiber cavity QED systems. So these are nanoscale devices. This diameter here is about 1 micron. So you can put many channel in your system. The system size of neutral atom QPU is about a millimeter. So you can put many in. And each are high quality cavity. So you can extract information or let atoms communicate with channels quite effectively. And you can directly connect with QPU. So what's nice about neutral atoms, you can move your qubits around physically. And what you can do is put atoms in this cavity QED, let it talk to each other in different modules, create entanglement, for example. And you can move it to the computational zone and do whatever you want to do, like repeater operation, entanglement swapping, or distillation, blind quantum computation, whatever you want. We've done some theory on the performance of these systems, and there is a good roadmap to go to 10 to minus 3 error rate with a kind of atom-atom behavior generation. That's our theory, so we have to do experiments. And the rate is expected to be hundreds of kilohertz with a cavity kind of quality we are expecting. So combining this with multi-channel solution, you can go up to pretty high networking rate that's compatible with the speed of computation. And for FTQC, operating at 10 to minus 12, 10 to minus 3 is quite noisy. So we have an idea on how to interface between the two worlds, from physical to logical operations, and the way to do it with what's called state injection in distillation. So you start with a physical bear pair, like entangled qubits. You inject that into a logical subspace of your logical qubit by state injection. That's quite routinely used for magic state. And you can distill that by the entanglement distillation. And in fact, people in Harvard have shown that starting with 10 to minus 3, you can go down to 10 to minus 12 with as low as initial less than 10 physical bear pairs. That's pretty impressive efficiency for network usage, even at 10 to minus 12. So I think that my question is what can we use that for in network architecture, say cryptography or blind quantum computation and so on. And I think that's an interesting frontier. So we have a bit of demo or POC going on in Tokyo. We have interesting data, and we are hoping to report that in archive pretty soon. So to summarize, neutral atom QPU are quite a promising approach for QC, and connecting these to network is another frontier that is going to be quite interesting. And we're looking forward to discussing what application we can do with these systems. Thank you very much.
How large do you expect your typical QPU to be?
So neutral atom QPUs are already at 6,000 qubits in a single module. And I think it's going to be 10,000 order. I don't know if you can go above that level because of some physical limitations like laser power and so on. So on the order of 10 to the 4 is a qubit number, a physical qubit number.
So, and that's why you want to have this top architecture to
exactly
exploit multiple such QPUs in parallel.
Right.
So how many do you expect to be able to run in parallel?
Depending on the architecture and problem you're solving, but with this, you can create, let's say, a few tens of probably logical pair per cycle potentially, and I don't know, maybe you can connect a single module to maybe a few different neighbors. How much you can scale that is depending on your network topology and your problem you're solving, whether that's like a dense circuit or it's more like a structured circuit. So yeah, that depends, I would say.
So I have another question, if no one has. At the software level, do you have a compiler that can target this kind of architecture?
I think that's only in academia. We don't have our own compiler yet. So yeah, that's another interest we have in terms of architecture design of these systems, both for FTQC and also network.
But you have graphics. You're the developer of graphics.
Exactly. Well, that doesn't give you this FTQC, so we have to, yeah.
Has the compilation of the algorithm to the distributed architecture, no?
For that's true. MVQC compatible, yeah. Protocol, yes. So that's a pretty good point. Yeah. Let's discuss. Thank Thank you very much.